Okay, as always, all the lectures are recorded. They'll be posted to YouTube. The lecture 1 video is up from what we did last time. I see a few of you have looked at that already, so you know where to find it. Remember, it is under the 2026 playlist. Okay, because if you just look at all the videos, it will be Math160, Math161 for all of the years. If you go to the 2026 playlist, it will just be our stuff. Okay, so you don't have to mix up anything. Okay, so we're going to be looking at integral definitions for functions. So those in electrical engineering, you might see a bit of this later on. Okay, it's used quite a bit. But this is just another way to define a function, but not like f of x equals x squared or cos x or sin x or anything like that. It's defining a function in terms of an integral. Now, we have seen these before. We haven't done much work with it, but they look like this. So, number 1, we have the natural log of x is equal to, now before we just had the natural log as a function by itself, right? Now we're going to define it in terms of an integral. So this is equal to the integral from 1 to x of 1 over t dt. Okay. Now, if you evaluate that right-hand side there, right, you get back to your natural log. Okay. So what we've done is we've taken the function and we've written it in terms of an integral. Okay, we call it an integral function. Now, this is just a very simple example. We'll look at other examples, especially the error function. You'll see that later on, which cannot be written in any other way. It can only be written as an integral. Okay. But for now, it will be a simple function like this. Okay, so what we want to do is prove some properties of the natural log using the integral definition. Yeah. So previously, when we looked at the natural log, we just had the properties given to us. Right? The natural log of x times y is the natural log of x plus the natural log of y. It was just given to you. You didn't really prove it or anything. Now we are going to prove those using this as our definition. It's just another way of looking at this function. So the first one, natural log of xy is equal to the natural log of x plus the natural log of y. We want to prove this. So you can start on either side, right? You can start on the left side, get to the right side, start on the right side, get to the left side. We're going to start on this left side here, and we're going to try get to that right side. Maybe for homework, you can try the other way around. Okay, so we're going to start on this side with the natural log of xy. And the goal is to write this first as the integral, then we're going to split it up, and then try get to those two parts separately. So using the definition, this is the integral from 1 to xy, right? Because if we just have the natural log of x, there's an x at the top. Over here, it's the natural log of xy, so we have xy at the top. Does everyone see the substitution we did? Okay. Then it will be 1 over t dt. Okay. Now, the idea is to split this up into two parts so that we end up with the natural log of x as one term and the natural log of y as another term. Okay. So we're going to write this as the integral from 1, right? That's our starting point. But the first term, we want it to be the natural log of x. So instead of going from 1 to xy, we're going to go from 1 to x for our first part, plus, what will the next one be? Not 1 to y. Remember, if we're going from a to c, it's a to b, then b to c. Yeah. Everyone on the side got it. So it's from 1 to x and then x to y. Perfect. Okay. Does everyone see how we split that up? Okay. So just on the side here, we have the integral from a to c, something dx is equal to the integral from a to b something dx plus the integral from b to c something dx. We used that property there. Okay, good. Now that first one is done, right? Integral from 1 to x, 1 over t dt, that's already the natural log of x. That's all sorted. Now the second one is not quite. We have x at the bottom. We want that to be a 1. We have xy at the top. We want that to be y. Good. So there's that factor of x that's annoying us there. So what can we do to adjust the bounds? We've got some old bounds from x to xy. We want some new bounds, that's the hint, from 1 to y. What can we do to change the bounds from the old ones to the new ones? U substitution, exactly. So we want a U substitution. Right, I'll just write it U sub. You know what that means. To change the bounds from, okay, so we have the old bounds, x to xy. Put that in red. To 1 to y. Let's put that in blue. Okay. So we have some U substitution where if we put the old bounds in, we get the new bounds out. So it's going to be U equals something, right? It's a normal U substitution. Something with t, right? That's our variable there. So what can we do so that if we put the old bounds into this U substitution, then we get the new ones? In other words, what's the difference from going from the old one to the new one? What did we do? We divided by x, exactly. So what does the U substitution have to be? T divided by x. Let's check. Okay, so we've got this U substitution. Remember, now we need to find du. So let's do that. So du. Now there's a lot of variables going on here. Don't get too lost. Remember, it's in terms of t. X is just some constant by itself. So this is du equals what? Ignore the x. X is a constant. We're doing this in terms of t. So du equals 1 over x dt. Exactly. Everyone see that? Okay. Replace x with the number 2. Right? Then you can see how it goes. Okay. But this is a definite integral. So we also need to change the bounds. So let's do that. So remember how it goes. T equals the lower bound. So u equals the new lower bound. So the old lower bound was x. We substituted in. What's the new lower bound? 1. Good. And now we need to change the upper bound. So the upper bound, if we go back here, was xy. We substitute that in. So u equals y. But this is exactly what we wanted, 1 and y. So that is the correct u substitution. So you can see it's actually correct. So let's do the u substitution, see what we get. So we had the natural log of xy is equal to this first term, which is just the natural log of x. We had that from the definition. Plus, and now we need to do the u substitution on that second integral. So the lower bound was x. The new lower bound is, what is it? 1. Good. We go back here. The old upper bound was xy. The new upper bound is y. So we can put a y here. The old function is 1 over t. The new function is? You sure? I'm not saying you're wrong. I'm just checking because if only one person says it, you can't be sure. Everyone agree? Oh, she does not agree. Okay, yeah. Oh, okay. Where did I lose you? Oh, the first step. Okay, if I lost you from the first step, you're gonna have to see me later. Okay. Yeah, just see me later. I'll go through it again with you. Yeah. But see if you can follow along from here. Okay. So the old function was 1 over t. We did the u substitution. So it's going to be something with u. So what will it be? If u equals t over x, then 1 over t will then be what? The little swap of variables. What do you get? Yeah, write it out. So u equals t over x. Do the swapping of the variables. What do we get for 1 over t? 1 over u times x. Yeah. Okay, so we do a little bit of working on the side. We can take the x over, right? Now we want 1 over t. So we do one more step. Okay, everyone see that? Yeah, so we put that in. So 1 over t becomes 1 over ux. Okay. Now what about the dt? Okay, so we've done the 1 over t part. Now the dt, what's that going to be? Again, do a little swap of the variables there. So du is 1 over x dt. What's dt by itself? X du, yeah. So let's write that here. So we got the 1 over t and we got the dt. So let's put x du. Now what happens to the x's? They cancel, exactly. So x at the top, x at the bottom. So we're left with the natural log of x plus the integral from 1 to y, 1 over u du. Now, does it matter what we call that variable? No, it doesn't matter. We can write this because it's a definite integral. That variable doesn't matter. We could say the integral from 1 to y, 1 over u du. We could say the integral 1 over y, 1 over t dt. It doesn't matter what we call that. So if we ignore the name of the variable, what is this integral? Go back up a little bit. If we ignore the variable, what is it? What's that? Natural log of y, exactly. So this we could have easily just written as 1 to y, 1 over t dt. That's exactly what we have at the top here, but instead of x we have y, so it's natural log of y. And we're done. That's the proof. Okay, so we just did the little integration property over here, just to split it up into the two parts, and then a u substitution. Okay, so just two things, not too complicated. Any questions about this? You're all good. Okay, I'll see you later for that. Okay, anything else? All good. Okay, so you get the idea of how to prove these. So for homework, you're going to do the other properties. So the natural log of x over y. So now we're doing the division of the two. So this will be the natural log of x minus the natural log of y. Okay. The idea is the same. You split it up into two parts, do the u substitution, and you'll get those two terms on the right. And then secondly, this one's probably easier. The natural log of x to the n is n times the natural log of x. Okay. So those are the three most known properties of the natural log. Please prove those in the same way that we did for the previous example. Okay. Any questions about the homework? All good. Okay, example 2. Yeah, so we've got this integral. There's a 2 over root pi in the front, but that doesn't really matter for us. Integral from 0 to x, e to the minus t squared dt. Okay. Now, in the previous example, we knew the natural log. It can just be written natural log. That's fine. However, this one, we cannot write this any other way. That integral over there, on the right there, is called non-elementary. It means there's no other way to write this function except that integral form. Okay. So the previous example was just a little introduction. This one, you cannot write it any other way. It can only be written as this integral. There's a few others that you'll see later on in engineering, but this is just a simple one for us to look at. Okay, we want to prove some of the properties. The first one, prove that this error function is an even function, is an odd function. Okay. You know what odd function means? F of minus x equals minus f of x. Okay, and we're going to do it a similar way with a u substitution. So to show something's odd, we need f of minus x to start off with. So we're going to look at the error function at minus x and try to get the minus out to the front. Okay, and it's going to be a u substitution like the previous one. So this is going to be 2 over root pi integral from 0 to minus x, right? Because we got minus x on the inside there. E to the minus t squared dt. Yeah. Oh. There we go. Okay. So, come on. If aircon's not working, projector's not working, students not working. Nah, you guys are working. Yeah, and working in this heat. I don't know how you're learning. And your other lectures, do you have aircons in those venues? Seriously? So it's all over that side. Eesh. Okay, it's back. Okay, so we got the minus x on the inside, and then we got the minus x at the top there. We want to try and get that minus out to the front, right, to show that it's odd. So that top bound there, minus x, we want that to just be x, right, to get the original function back. So what kind of u substitution can we do to change the minus x back to x? No, not with x. It must be in terms of t. Remember, everything's in terms of t. X we just treat as some constant. So it will be u equals something with t. Any ideas? So we want to go from minus x back to x. What can we do to flip the sign? Yeah, if I give you minus 2 and you want to get to 2, what do you do? Sorry, times what? Times by negative 1, yeah. So let's say we have... now the pen's not working. Okay, yeah, we times by negative 1. So if we say u equals minus t, right, times by negative 1, what happens to the lower bound if u equals minus t? Stays 0. Yeah. What happens to the top? Becomes x. Yeah, exactly. Okay, so we're going to have u equals minus t. In other words, we just multiply by -1. So let's see if this works. We're going to have to find the du. So du is minus dt. Take the minus over to the other side. So minus du equals dt. Yeah, but it's definite, so we need to change the bounds. So the bottom bound is t equals 0. If we substitute t equals 0, u equals 0, so that stays the same. And if we say t equals minus x, u equals minus x, so it's just x. So this becomes 2 over root pi, integral from 0 to x. Then it will be e to the minus t squared, but t will be minus u. Okay. And then dt, that is minus du. So we put that in. Now in the exponent, it's minus u squared, so that's just u squared. And then the minus from the minus du, we can just take to the front. And again, it doesn't matter what we call that inside variable, u, t, doesn't matter. All of that stuff, except for the minus sign, is what we started with. Okay, so what did we start with? Let's go back up here. We had the function at minus x, and this equals minus the function. That means it's odd. So our function's odd. Everyone see what we did for this? All good. Okay, last one's going to be for homework. So we have the integral definition for arctan. Okay, you can do this integral definition for lots of functions. Here's for arctan. Okay, you've seen this before. So we have from 0 to x, 1 over 1 plus t squared dt. Okay, remember what this looks like if we do a little sketch. Okay, remember the arctan function from last year? So when this x goes to infinity, then this goes to pi over 2, and the other way it goes to minus pi over 2. Right, because tan of pi over 2 goes to infinity, so arctan going to infinity is pi over 2. It's the inverse functions. Okay, so remember this. You'll need that there. Okay, so we've got this integral definition. Prove the identity. Okay, arctan of 1 over x. Okay, so we flip the x. This is equal to pi over 2 minus arctan of x. Okay. I think we did a similar identity to this last year. You don't need to know how to get this identity because we're going to use this integral definition now. Okay, so you start with that left-hand side. You replace x with 1 over x. You do the u substitution, you split it up, and you'll get back to arctan x. Okay, everyone clear on what to do? All good. I hope so. Please keep this in mind for the quiz. Okay, so this first section, hint, hint. Okay, everyone clear on this topic? All good. Okay, next, integration by parts. So we're done with u substitution now. So for the quiz coming up, it will be the u substitution from end of last year. this little bit of new U substitution we've done now. So that will be for the quiz and for the class test. And then this will be it for U substitution. Okay, so we're not going to do any more of that. Okay, the next topic and the next integration technique is integration by parts. Okay. So U substitution, that was the first integration technique. We're done with that. Integration by parts, we'll finish that this week. And then next week, we will start on the other integration techniques. Okay, so most of this semester will just be on these integration techniques. Okay, so recall the product rule. Okay, so remember what that was. If we have uv prime, so the derivative of u times v, this is equal to the derivative of the first one, we leave the second one alone, plus we do the derivative of the second one, we leave the first one alone. Okay, so everyone remembers the product rule. Okay. So what we're going to do is undo the derivative using an integral. Remember, FTC from last year, those are inverses. So we're going to do the integral of all of this, undo the derivatives that we have there. Okay, so this is going to be the integral of the derivative. So I'm going to write it integral d by dx u times v is equal to the integral. Now this one, instead of u prime, I'm going to write it as du by dx. Just makes it a bit clearer. Plus, and then the integral, instead of v prime, I'm going to write dv by dx. Again, just makes it look a bit clearer. Okay. Now for the first one, the integral and the derivative, they cancel. Right? They're inverses. So here we get u times v. Now for the next integral, we've got v du by dx dx. So what we can do, cancel the dx's there. That's just a little notation bit there. We can write this as v du. Now there's a long way to do it with u substitution and all of that. We're going to avoid that. Just cancel the dx's, we have v du. And then the last one there, similar idea. You could have done a u substitution and all of that. We're not going to do that. We're just going to cancel dx's like that. So that's going to be plus the integral u dv. Okay. This is a very, very important formula. Okay, it's the integration by parts formula. Now, we're not going to write it like this. We're going to make one more modification. Then please put a big box around it and as many stars as you can fit on the page. So a little bit of rearranging, we get the integral u dv. That last term there, we're going to keep to one side, and everything else we're going to write on the other side, is equal to uv minus the integral v du. So we're not going to use that form there. We're going to use this one that's slightly rearranged. Now this one, please put a big box around that. Okay. Now, I'm not a big fan of just memorizing things. However, this one you have to memorize. Okay. Even though your class test 1, 2, and June test are open book and you can look back and so on, just memorize it. Trust me, it will do you a lot of good memorizing it rather than flipping back in your book to see what the formula is every time. Okay, so there's only a few times I'll tell you, memorize the formula. This is one of them. Okay, please make sure you memorize this. So integral u dv equals uv minus, and then we swap the u and v. So it becomes v du. Okay. Again, please memorize that. So this is the integration by parts formula, and it's used when we have integrals where we have a product of two functions. One of the functions we're going to call u, the other function we call dv. We split up the integral into two parts, integration by parts. Then on that right-hand side, if we swap the derivative from instead of being on v, dv, we now swap it to u, now we get du. The hope is that when we swap those derivatives, that right side becomes easier. It may not become easier in some cases, but again, it's always about hope, right? All of these integration techniques is just hope it becomes easier. Okay. So the idea is to swap the derivative from being on u, on v for the dv, to being on u. So here the derivative was on v, we had dv by dx. We swap it over to the other term, and now we have du by dx. And again, we cross our fingers and we hope that that second term there is easier to work with than this first one. Okay, that's the idea. The best way to learn this is by examples. So we're going to do quite a few of those. So example number 1, we have the integral of x e to the x dx. This is always the first example to look at. Okay. Now, it's not always a guess on what u and dv are, right? How do we split it into the two parts? There's some fixed rules we can use, some not so fixed rules. But the idea is to choose u to be the part that we can differentiate, right? Because if we look back here, u becomes du, right? We're going to do the derivative on u. So whichever term we pick to be u, when we do the derivative, we hope that it's simpler. So rule 1, we pick u so that du by dx is simpler. Right? If you differentiate it and somehow it becomes more complicated, that's probably the wrong thing to do. Now, in this case, we look at these two, x and e to the x. When we differentiate x, what does it become? 1. That's pretty simple. When we differentiate e to the x, it becomes e to the x. That hasn't changed. So between the two, which one becomes simpler when we differentiate? X, so we pick that one. Okay. Now, if that doesn't work, we look at rule 2. We pick dv such that it's easier or easy to integrate. Okay, because remember, dv is becoming v, we're integrating. So between these two rules, picking u or picking dv, you should have a good idea on how to split this up. So here, we can use rule 1, x is easier to differentiate, so we don't have to worry about the other parts. Okay, does everyone see that? So once you pick your u is x, dv is everything else, right? U dv. We picked u, so dv is everything else. So let's rewrite this. So we're going to have u equals x. That's what we picked, u equals x. Now we still need to have dv, right? This part here. If u is x, dv is everything else in the integral. And we write it on the side here. You see how we split it up into the two parts? Okay. So we're going to make a little table now. So we have u equals x, dv is everything else. Now, what do we want for this right-hand side? We want v and du. So here we got u. Let's find du. So du equals, what is it going to be? 1 dx. Remember, it's the differential. Okay. Right, du is du by dx. Don't leave that out. Okay, and then on the other side, we have dv, but we want v. So let's integrate. So the integral of dv, that's just v. What's the integral of e to the x? E to the x. Yeah. Now here, we put another big warning. Okay. This is where a whole lot of confusion comes around. For that first part of the table, we are doing derivatives, always. So u becomes du, we are doing a derivative. On the right side there is an integral. Now the problem comes, what happens if u is sine x and dv is cos x? You tend to mix up the minus signs. On the one side is a derivative. You need to follow the derivative rules. On the right-hand side is an integral. You need to follow the integral rules. If both of those are trig functions, you need to keep in mind that on the one side, it is the derivative rules for the trig functions. On the right-hand side there is the integral rules for the trig functions. There's always that minus sign difference. Do not mix up your derivative rules on the one side with the integral rules on the other side. It's very easy to mix them up when you're acting quickly, rushing through a test. So please put a big warning there. Do not mix up those two parts of the table. Because you mix that up, everything after that is wrong. Now, if everything after that is wrong, you get a nice 0 for everything. There's no part marks I can give. Everything's wrong afterwards. Yeah. So we set up the table, and then the next line is the integral formula we had above. So that is the integral u dv equals uv minus integral, what is it going to be? V du. Good. If you say it a lot, you tend to remember it easier. Okay, so let's substitute. So on the left side, u dv, that's going to be our x e to the x dx. Now, u times v. We're going to look at the top corner and the bottom corner. We've got u from the top and v from the bottom. So you look at this diagonal. That gives us u times v. That will be x e to the x minus the integral v du. Now we look at the right side and the left side. That will give us v du. Okay, so you look at the diagonal to get uv, and then that bottom there, v du. Okay, seems like a lot, going through it step by step, but when you're actually doing the problems, it's actually quite quick going through it. Okay, now remember why we did all of this? The hope was that that integral on the right side is easier than the integral on the left. Is that true? So the one on the left, we had no idea how to do that. On the right is now integral e to the x dx. That's much easier, right? What's that integral? E to the x. Very easy. You didn't have to do any working. So this will be x e to the x minus e to the x. And once we're done with everything, plus c. Okay. Everyone get an idea of the method? So you set up the table, you use the formula, and then you got one more integral to do on the right. So set up the table. Sub into formula. And finally, solve the integral on the right. Okay, 3 steps. Let's have a look at another example. Number 2. We have the integral of x squared cos x dx. Okay, so we'll go through it step by step again. We need to choose u and dv. U is something that gets simpler when we differentiate. dv is something that we can integrate. Between those two, we can make a pick on what it's going to be. Now here we need to decide between x squared and cos x. One of these is going to get simpler when we differentiate, and then the other part we're going to call dv. So between these two, which one is going to be u? X squared. Good. Now we picked u, so dv is automatically everything else that appears. And again, I'll put the warning sign because we've got cos x on that side of the table, which means we are integrating cos. So we need to remember, the minus signs, which one gets the minus. Okay, so on the first one there, u equals x squared, we need du. What's that going to be? 2x dx. Good. And on this side, we integrate. So we get v equals, now we need to be careful again. We're on the integrating side. So the integral of cos is sine. No minuses anywhere. Okay. Everyone clear so far? All look good. Okay. Next, we use the formula. Again, you say it a couple times, you'll remember it. So integral u dv equals uv minus integral, what's it going to be? v du. Very good. Okay. And then we substitute. u dv, that's going to be our x squared cos x we had at the beginning. uv, we look at the diagonal. So it will be x squared from the top, sine x from the bottom there. So we just write x squared sine x. Then comes the minus, integral. Now we need v du, so we look at that bottom part. So it will be v du. So we have 2x and a sine x. Now we have a little bit of a problem. Yeah, so we did all of the integration by parts. Everything's fine. Slight problem here. What's the problem? We have to do it again, exactly. Okay. So we look at that box there in green. We see, forget the 2, it doesn't matter. We see x sine x. That's still a product. We're going to have to do integration by parts a second time. So don't think, okay, this technique, you do it once and we solved it, like with u substitution. Sometimes you have to do it once, like the first case. Sometimes you have to do it twice. I'm not going to give you a problem with 3 times. That's just mean. So twice. Other times you have to do it once and then you have to do a u substitution. They get mixed up. Okay, so please just make a note here. So sometimes you use integration by parts once, like we had in the first example. Okay, sometimes you have to use it twice, like in this case. And sometimes it's a mix. So you do integration by parts once, and then that integral on the right side there, you then have to do a u substitution on that. Okay, so please make a note here. So this is to avoid you thinking one problem is one technique. No, that's not the case. One problem can use two techniques. Later on in the semester, we'll see a problem where we start with a u substitution, we end up with an integration by parts, and then we have to do a trig substitution. Right? You can have three techniques for one problem. Okay, so please, from now, don't get the idea one problem, you do u substitution, it's solved. You do integration by parts, it's solved. No, it's always going to be a mix. Sometimes it is easy, sometimes it's more difficult, but expect things like this, where you use one technique and then use another. Okay, so let's get back to this one. So let's look at this integral, integral 2x sine x dx, and we're going to do integration by parts again. So I'll just put a green dot here. We're continuing with that integral. Okay. What do we let be u and what do we let be dv? Between the two terms there, which one is easier to differentiate? The 2x, yeah. So we're going to let that be u. And then dv, that will be everything else. So we need du. That's just going to be a 2. Integrate, integrate. So v. Again, warning, this side is integrating. So we're integrating sine. That will be negative cos. Good. Again, just always keep in mind, what are you doing on the one side? What are you doing on the other side? Okay, let's set up the formula. Integral u dv equals, what's it going to be? uv minus, very good. I think most of you have memorized it by now. Okay, we substitute. So u dv, that will be our 2x sine x we started with. uv, we look at this diagonal here. So we have a 2x and a minus cos x. Then a minus, and then the integral v du. So we look at the bottom part here. So we have a 2 and a minus cos x. Okay, for that integral, we've got 2 minus signs, so let's just rewrite that with the plus. Okay, what's the integral of cos? Sine, good. Yeah, so we've got that. But we're not done. All of this calculation was just for the green box. Okay, remember, we still have this. So don't think, oh, no, we're done with the second parts. No, that was just the side calculation. So let's put the final answer down. So integral of x squared cos x is equal to what we had at the beginning, x squared sine x minus, and then in brackets, it's all the stuff we did for that side work. So just above there. You can put the c on the outside there. So this is going to be x squared sine x, minus and a minus, so there'll just be a plus, and then a minus. Okay, you see we have more terms now because we had to do it twice. All right. Any questions for this example? Okay. So now we're going to go back to this rule number 1 we had here. We pick u so that du by dx is simpler. In this first case, we picked x. In the second case, we picked x squared. So in general, a good idea for u is whatever polynomial part we have for the integral. So we're going to just expand on that rule 1. So a good idea for u is any polynomial part of the function. Okay. So if you have some polynomial part, so like x squared plus 3x, for example, that polynomial part you let be u. And then everything else, that will then be dv. This doesn't work all the time, right? Sometimes we go against the rules, but it's a good idea. Okay, so again, just underline here, good idea. Okay, so it's not fixed, it's not set in stone. You always pick the polynomial part. It's a good idea to pick the polynomial part. We'll see maybe later today if we get to it. Sometimes you don't pick the polynomial part. Okay. So you just need to see what you're working with. Okay, everyone okay so far? All good. Okay. Next, something that will help quite a lot with these problems, especially when you need to do it multiple times, is something called the table method. Does anyone see the table method when you were doing your pre-reading? No. Okay. Okay. So the table method is very useful when you can see that you're going to be doing integration by parts multiple times. If you're only going to do integration by parts once, it doesn't give you any advantage. If you're going to do it 2 or more times, it's quite helpful. So we're going to do this table method for this example here, where we had to do it twice. And we'll see it makes it look quite a bit easier. So example number 1 is just a repeat of what we had before, but now we're going to use the table method. Yeah. So same thing. It starts out the same. We're going to pick u and dv. But now instead of completing this table we had before and subbing into the formula and so on, we're going to set up a different table. So it's the dr table. D stands for differentiate. Down that column, we're going to differentiate the function again and again for each row. I stands for integrate. Down that column, we're going to integrate the function for every row. So we start off with x squared and cos x. And we're going to repeat the process of differentiating and integrating, and there's going to be a cutoff point. We'll see where that's going to be. So down the first column, that's D for differentiate. X squared becomes 2x. 2x becomes 2 becomes, and we can stop there because the derivative of 0 is 0. You're just repeating yourself from that point. Now down the I column, we're going to integrate. The integral of cos is, the integral of sine is, and the integral of minus cos is minus sine. Okay, we can stop there. Now what we're going to do next is match up the diagonals. So it's the first one from the D column and the second one from the I column, right, to make the diagonal. So we're going to match up these diagonals. So x squared with sine x, we're going to match those up. 2x with minus cos x, we're going to match that up. It's always going down the diagonal like that. Then 2 with minus sine x, we're going to match that up. Okay. Everyone see what we got so far? Okay. Now, if we look at these diagonals, let's look at the first one, x squared sine x. We go back up a little bit. X squared sine x, that's the first term we had in our answer before. Okay. And then 2x with the cos x, they match up and so on. But not exactly like that. The signs alternate as we go down. So down the side here, we write plus, minus, and so on. Okay, we need to include those signs when we match them up. Why? Well, if we go back to the formula here, we see we have this minus sign here. So every time we do the by parts integration, we get a minus sign. We do it again, we get another minus sign. That makes a plus. We do it again, we get another minus sign. That's back to a minus, and it alternates every time. So every time we do by parts, we get a minus sign going through. Okay, so we've got plus, minus, and so on. So the first term, it's a plus x squared sine x. So we write that down. Okay, you don't have to write the plus in front of it, but it just shows you that we're using the plus. So 2x times minus cos x is minus 2x cos x, but we got another minus there. So that will be a plus. That's the second term from our answer. Next one, we have 2x and a minus sine x. That comes with a plus, so it stays minus 2 sine x. If we go back up a little bit, minus 2 sine x, that was the third term. Plus c. Okay. So we have the full answer just from this table. Instead of doing integration by parts once, and then doing integration by parts another time and adding the answers, now we get the full answer in one go. Now, you don't have to use either method. I'm not forcing you, but this method is quite helpful. Okay. Does everyone see what to do? You get the idea? Okay. So for homework, yeah. You can use it whenever you like. It's just something you can use. So you can do it the first way, you can do it the second way, you can do it both ways, up to you. So homework, integral x cubed e to the 2x dx. Now here, it is x cubed. That gives you a hint as to how many times you have to do by parts. When we had an x, it was once. When we had x squared, it was twice. X cubed, you can guess you'd have to do it 3 times. Please do this both ways. The first way to show you how long it is, and you don't want to do it that way. And then the second way, using the table method to show it's much quicker. Okay, so homework, try it both ways, and then match up your answers between the two. Okay, any questions for the homework? All good. Okay, and then the last bit of homework before we get to the next section is the integral of e to the x cos x dx. Okay. So this one makes it a bit more difficult choosing which one is u and which one is dv. Because if we choose e to the x to be u, the derivative is just e to the x. It doesn't really help us much. If we choose cos x to be u, then the derivative is minus sine. That still doesn't help us very much. In this case, it doesn't really matter which one you pick. Okay. They're both just as bad. Okay. Yeah, it's not just as easy, but it's just as bad. So what you're going to do for homework is pick one to be u, one to be dv, go through the calculation, and try and simplify to some final answer. Okay, so I suggest you do it one way, so pick u and dv, and then swap it, see if you get the same answer. It's about the same working for both. Okay, but it's a little bit more difficult. So this one we'll go through beginning of Thursday. I'll show you how to do it. Okay, but please for homework, try it out first. Okay, last thing for today, integration by parts, but for definite integrals. So all of these examples here were for indefinite integrals. Now, what happens if we add bounds to it? There's one more step we have to do. So everything's pretty much the same. It's just one more step because we have the bounds to worry about. So recall the formula. So we have the integral u dv is equal to uv minus integral v du. The only thing we're going to do now is add the bounds. So we're going to have from a to b. Then we're going to have this term evaluated from a to b. You know what those brackets mean. And then the last one is from a to b. That's it. That's all we do. Okay. So going from indefinite integrals to definite integrals, you just put the bounds back. Everything else is exactly the same. Okay. So we'll do one example with the bounds, and then we can go. Okay, so we'll do the one we started with, but now just going from 0 to 1. Again, everything else is exactly the same, so I'm just going to copy that down. So u will be x, dv will be e to the x dx. We want du, so that will be dx. We want v, that will be e to the x. So everything else exactly the same, I just copied it over. So now we have the integral from 0 to 1. X e to the x dx is equal to, but now we've got the brackets for the bounds, and we have u times v from 0 to 1 minus the integral from 0 to 1 v du. Okay, so the only thing different is putting in the bounds there. Okay, so now let's evaluate. So at the end, we're going to get a number, right? Because it's definite. So if we put in 1, we get 1 times e to the 1 minus, and if we put in 0, we just get 0. And this integral of e to the x is e to the x from 0 to 1. Okay, so what do we get for this one? Sub in the bounds. E to the 1 minus 1. Yeah. So this will be e to the 1 from the first term with the upper bound minus e to the 0, that's 1. So minus and a minus, that makes a plus. We just get 1. Okay, so again, we just get a number at the end because it's a definite integral. Okay, I won't do any more examples. It's already past an hour now. Everyone okay with this example with the bounds? Okay, so it's exactly the same as the other examples, but you just put the bounds as you do the working there. Okay, so we'll leave it at that for today. Please, for the next lecture tomorrow, please read through integration of inverse functions. So if you look in the textbook, after this introduction bit on integration by parts, the next chapter, subchapter is with inverse functions. So please read that for tomorrow. So integration with inverse functions. Okay, so you'll see this as one of the examples in the textbook. Okay, so just read up to this first example. Please just see how to do that. And then on Thursday, we'll finish off with that chapter. Okay, any questions? Yeah. And then just one last thing. I see a lot of you have not filled in that module rules form. Please make sure you do that before the quiz. Otherwise, you're not getting your marks. Okay, you have to accept the module rules and procedures before your marks can be released. Okay, so here, just go down here, modules, rules and procedures forms. Okay, you just click that, a little bit to read through. You know all of this from last year already, so it's exactly the same. Just read through that, fill in your details, and then just click this agree here. Okay, so not many of you have filled that in yet. I think, yeah, 37. It's just over half. Okay, please make sure you fill that in. Otherwise, your marks will be withheld. Okay, starting from next week when you do the quiz. Okay. First year's 8. Okay, a little bit better for you guys, but please make sure you fill that in quickly. Okay. Any questions before we go? Okay. I also heard the temperature is going to be like 32, so please make sure you drink enough water. Okay, we don't want you fainting in the lectures.